Hello, dear students. Today I'm going to take up a really good Allen AITS question. Okay, this question has concepts from laws of motion, friction, rotation, magnetic field. So I thought at this juncture it will be a good concept revision question for you all. Also, I saw the solution and felt that if I can explain it in detail, it would add more than the what is given in the solution. The solution does not do justice to the depth and the beauty of the problem that is given. Let me first explain you the question. There is a cylinder, hollow cylinder here, and there is charge distributed uniformly on it. Okay, so you see here on the surface there is charge. There is a magnetic field in the upward direction, and this floor there is friction. Okay, the question that is asked is, what is the maximum speed that this cylinder can go, while in pure rolling, and on the ground like this. It should be on the ground, it should be in pure rolling. So what is the maximum speed that it can go? Okay, so let us move into the solution for this. See, before we move on to solving this question completely, let us go step by step. First, we'll find out what is the magnetic force and torque on the cylinder. We'll mark it using arrows so that there is clarity when we start solving the question. There is a magnetic field in the upward direction and this cylinder is rolling. Okay, first let us look at the force. So I have divided into translation plus rotation. Okay, so what is the force? Tell me. F equal to, see, all the charges here are moving with V here. So V bar cross B bar, there is a force in this direction. So you can see I mark the forces in this direction. So force equal to QVB. Okay. All the charge has speed V. So directly we can write this. Okay. Next, consider rotation. Here the force is V bar cross B bar, force is outward. Here the force is inward. So at all these points, force is outward, all these points, force is inward. So the net force on this due to rotation is equal to 0. We'll combine them again vectorially. Okay. The next thing, torque. Okay. So these force which is outside, if I take torque about the center, the net torque is 0 because force is distributed equally everywhere. Now let us see for this, what is the torque? See, this is rotating. Okay. So we already know the formula for this. Torque equal to M bar cross B bar. Okay. Now, if it is rotating in this side, this is like a current loop. So M bar is in this direction, B bar is upwards. So M bar cross B bar, there is a torque in this direction, and M bar and B bar are perpendicular. So I'll just write the magnitude. Torque equal to M into B. So torque equal to, what is M? Current into area. So current we can directly write as Q omega by 2 pi. Q into frequency is the current into area. What is the area of this loop? Pi r square into B. Okay, so I'll just write this. Torque equal to pi cancel. I'll write this omega as V by R. Okay, V by R into R square into B. So torque equal to QVB into R by 2. So net magnetic force on this cylinder, if it has center of mass velocity V, is QVB. Okay, and the net torque on this is QVB into R by 2. Okay. Next, what we will do is, we want to replace all these forces with a single force so that we can get net force and equivalent torque. Why I'm doing all this is, you get a clarity, what is the direction of forces, what is the direction of torque. Okay. So now if I combine these two, see the force here, all the force in this direction, here on top force is this side and on down force is inward. So if I combine the forces, I'm going to get force like this on the cylinder. Okay. And what is this net force equal to? This net force is Q into V into V in this direction. Next, we look at the torque. See, this is a distribution of force here. We want to replace it with one force so that it is easy for us to work in the free body diagram. So, what is the torque? Tell me of this force. The force is equal to QVB, and the torque about the center is QVB into R by 2. So, what we'll do is we'll just replace this with one force, QVB, at a distance R by 2 from the central axis of the cylinder. Okay. Now we don't need to worry about magnetic force and magnetic torque. We'll just write this one force and that will take care. Okay. Next, let us look at all the forces acting on the cylinder as it is rolling. Okay. Gravitational force in the downward direction, normal force in this direction, a QVB magnetic force in this direction. Okay. And because what will happen, this will tend to move this side, there will be a friction acting in this direction. Okay, so these are all the forces acting on the cylinder. Next, what happens when the velocity of cylinder increases? Okay, let us see here. See, the cylinder is here. The cylinder is rotating fast and slowing down, and we'll see how the forces are changing here. Okay, you see, as the velocity speed is increasing, the QVB is increasing in this direction. Okay, and because this QVB is increasing in this direction, you see the friction here is also adjusting and increasing in this direction. Okay. Next. Now about the center, the QVB and friction, there is a torque in this direction. It wants to rotate the cylinder in this direction. So to balance that, the normal reaction, it is going away from the center and balancing the torque created by friction and this thing. Okay. So you see there are multiple cases that could happen here. As the V is increasing, suppose if friction reaches its maximum value, okay, before the normal has come here, then it will start sliding. So the V max will be when friction reaches maximum. Suppose as the normal keeps coming here, if it comes almost here, then what will happen? The cylinder will tip off like this. The whole cylinder will lift off. So that would be the maximum velocity. So there are different cases here, and we'll look at each case and solve for the maximum speed of the cylinder. So let us look at the different cases. So look at this diagram first. What is happening is as this is increasing, the normal goes and comes to here. If it goes any further, this whole thing will lift off like this. So the first case is that tipping is taking place before friction reaches maximum value. Okay, greater, I mean it is happening before the friction reaches maximum value. That is one case. And you see the second case here. F is reaching maximum before the normal could come here. Okay, so F is reaching maximum before the tipping. In such cases, we have to stop it here. If the speed increases even further, QVB will increase. Okay, friction is maximum, so it will start sliding like this. Okay, so we cannot increase it further. In this case, if we increase QVB, this torque about center will increase and this whole thing will lift. Okay, so for each of these cases, we have to independently see what is the maximum velocity. So let us take the first case. The tipping happens before friction reaches maximum. So what can we say here? Tell me. Friction is less than mu n, which is equal to mg. Friction is less than mu mg. Why? Because it has not yet reached the maximum. Okay. Next, what we can write is F equal to QVB. Because it is not accelerating in this direction, we can write F equal to QV into V. Okay. Now it is also not rotating. Okay. So if I take torque about this point, okay, there is no torque due to friction, no torque due to normal. the torque due to QVB must be equal to the torque due to mg. So what is the torque due to QVB? QVB into, from here it is r by 2, so from here that is 3r by 2 must be equal to, due to this it will be mg into, the length he has given capital L, okay, L by, okay. So I can substitute this here and just write F into 3R equal to mg into L. Okay. So this F is lesser than mu mg. So I can write mgl by 3R is lesser than mu mg. So from this, what can I say? Tell me, I'll just cancel out these two and I'll get L lesser than 3 mu into R. So basically L lesser than 3 mu R corresponds to the condition where tipping is before friction reaches the maximum value. Okay. So for this case, what will be the V maximum? Tell me. So at this condition, V will be maximum, right? So we are looking at L less than 3 mu R. We are looking at these two cases. Okay. And from here, we can see what will be the V. This will be the maximum, right? So V max will be equal to, from here, mgl by divided by 3qb. Okay, so you can see here this A will be the correct option. Next, let us look at the condition friction reaches maximum before tipping. That means this become maximum before this normal goes here. So what can we say? If this has reached maximum, I can say F equal to mu mg, right? And yes, F is also equal to qvb. Next, if I take the torque about center, okay, again the net torque is 0. So torque due to QVB is, so I'll just write here torque net equal to 0. So QVB into R by 2 plus, what is the torque due to friction? Friction into R, right? Friction is also QVB, so that is QVB into R equal to normal reaction into this X, N into X. Okay, so I can just simplify this. I can write this as 3 QVB into R by 2 equal to mg into X. Okay, now if this tipping is occurring after, can we say this X must be lesser than L by 2? Normal should be this side, right? So this X must be lesser than or equal to L by, so I'll just put X from here. What do we get? 3 QVBR divided by 2 mg must be lesser than or equal to L by 2. Okay, just cancel out these two, and we know again QVB is nothing but mu mg. I'll just keep that here, 3R by mg into mu mg lesser than or equal to L. Okay, mg you can cancel and we get the condition for L greater than or equal to 3 mu R. So basically this is the case. This case corresponds to L greater than or equal to 3 mu into R. And so what is the maximum speed? So at this instant the speed is this one. So I can directly write for this the speed V equal to mu mg divided by q. Okay, so L greater than or equal to 3 mu R, the Vmax equal to mu mg divided by q.